Hey everybody, Mr. Piercy here, and this video is talking about geometric probability. Probability in and of itself is just what are the odds of something occurring. You guys, as young adults or children, may be familiar with odds of like asking your parents for a favor, like, have you cleaned up your room? Did you do the dishes? Did you walk the dog? That kind of thing. And then you're going to ask, well, I did all of my chores. I did all this, I had my good grades. So if I ask for, insert, fill in the blank with whatever you ask for here, then the odds are maybe going to be in my favor. I don't want to go quote the Hunger Games and say, may the odds forever be in your favor. But anyway, that's all probability really is. It's just the likelihood of something occurring. Maybe the likelihood is very high because of certain elements, or maybe the probability is fairly low because of certain elements. And the more variables that you include when you're talking about probability, typically the greater range of possible outcomes that you might have are. So when you talk about there's I can't think of the name of it off the top of my head, but there's an equation that astronomers and astrophysicists use about what are the odds of the possibility of life being on another planet, and they have all of these all of these variables that they have to take into account as far as like, where is it in the solar system, and what are the odds of them developing technology? What are the odds of them not blowing themselves up with that technology, and then being able to develop the technology to be able to get in to communicate with somebody outside of their system, and things like that. So the more variables that you include in any given system can drastically change the possible outcomes of something, or the percentage of something happening. So geometric probability is really just a ratio. So it's nice because it's typically only going to involve two variables. Something where we may be looking at comparing what are the odds of it being on this length versus another length, or this piece of the segment versus the entire segment, or when we look about area. So we can look to see, okay, well, I have a dartboard and I want to be able to hit this particular section. So what are the odds of me actually throwing a dart and hitting it? So we can figure out, for something like that, we can actually figure out what the geometric probability is. But then there's the added variable of how well you can actually throw a dart. So, like I said, the more variables you include into a system, the more it changes the likelihood of something happening. So here we have a couple of examples of just what probability are. The two on the left are specifically talking about geometric probability, and the one at the bottom is just kind of showing you possibilities. That's something about probability. So uh, anyway, let's go ahead and move on. So here, this is how we find the probability of something being on a certain piece of a segment. So here you can see that we have a segment from A to B, and it's broken up with point C and point D. So we actually have quite a few segments here: AB, AC, AD, CD, and so on. So we want to know what's the likelihood, or what is the probability that point K, some random point, is going to be on segment CD. Well, we could just, maybe this is on a number line, maybe this is, on a ruler, but we're only looking at just this piece here. What are the odds of picking something that's going to be on just that piece as opposed to the entire thing? So that's how we're kind of looking at the probability of something being on segment CD as opposed to anywhere else on AB. It's a ratio of those things. Now, the one thing that I want to add here, generally when you're talking about probability, no matter what it is, the most common thing is when we think about it in terms of grades. Okay, so let's think about our grades, right? Your grades are just a ratio of your points, I can't write, points earned out of the total number of points available. So let's say there's, let's just say that there's total of 10 points available and you got 8 of them. So that would simplify to be a fraction of 4/5 or 0.8. Now, on your grades, we don't look at, well, we don't say you got 0.8. We say you got 80%. So the ratio that we earn or the ratio that we get when we're looking at probability is generally going to be a number that's less than 1, some decimal number. So when we convert it into a percentage, you remember you have to multiply by 100. So here, multiply the percent, oops, not multiply the percent, but multiply the decimal. Whoa, that was big. Didn't mean it to be that big. Multiply the decimal to get it as a percent. So, moving on, find the probability that a point chosen at random on segment FJ is going to be on segment GK. Well, if we look from segment FJ, we're looking from here to here, which is a fairly long segment. And you can just kind of count to see how long it is on the number line. So we're counting by ones. So from F to J, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spaces long. And we want to know what's the odds that something from G to K is going to be on the entire thing from F to J. So again, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are the ratios. Those are the two numbers that we're going to look at as a ratio. Now, the way that they're having us fill in the blanks here, so we're still looking at GK to FJ, the part versus the total. And that's another thing that we can look at here. Generally when we're looking at a ratio for probability, we're always going to be looking at part over the total, and again, times 100 to get it as a percentage. So here, the length of GK, they're using the ruler postulate to show that the overall length, it doesn't matter which direction that we go, the absolute value difference is going to be whatever the length between the 2 points is, because distance can never be negative. But again, we get the 9 over the 12 that we just counted. So 9 over 12 simplifies to be 3/4. So as a decimal, it's 0.75. So that means when I multiply the 0.75 by 100, 75%. So there's a 75% likelihood of randomly picking a segment that would be on GK that's on segment FJ. So there's a 75% chance of that happening. Now here, this is kind of an odd looking one here, but I like the idea of it. It's not necessarily going to be so much of a geometric probability really, but it's still talking about the likelihood of something happening, and we can apply numbers on a number line. So that's kind of how we're looking at it from a geometry standpoint. But a shuttle, like a bus, or maybe just something that takes you from a hotel to an airport or something like that, or if you're staying at a hotel, sometimes they'll have shuttles that run you to, say, an amusement park in the area, or a museum in the area, or something that's going to take you to an arena so you can watch an event, whatever the case is. But a shuttle to town runs every 10 minutes. The ride that it takes you to go from wherever you're going into wherever town you're is, a downtown or whatever venue that you're going to, the trip is going to take you 13 minutes. So you arrive at the boarding location at 2:41 in the afternoon, I'm assuming, because it would be kind of weird to be arriving there at 2:41 in the morning. And you need to get to town by 2:57 for some reason. That's a very specific time. What is the probability that you get there by 2:57? Well, the way that we're going to look at this, looking at step one of our solution, the longest that we can wait for the shuttle and still get to downtown by 2:57 or get to town, since the ride takes 13 minutes, and you can't wait, the rides are no more than 10 minutes long, first of all, we're going to subtract the time that you got there from the time that you need to get there. So since the ride takes 13 minutes, we're going to subtract the 13 minutes from 257, where we're getting that 244 from. Well, you got there at 241. So the longest you can wait is 3 minutes and still have the opportunity of getting to your destination on time at 257. So here again, they're kind of modeling it on a number line from 241 to 257. This is when you arrive, and this is when you have to be at your location. Well, since there's a 10-minute window of time that you have to wait for potential rides, the only window of time that will work for you to get to your destination at 257 is this 3-minute window here. So those 3 minutes out of the total 10 minutes that you have says that there's only a 30% chance of you getting to your destination on time. So that's what they're kind of looking at here. Again, they're putting it on a number line, kind of an odd situation, but it still kind of works for a geometry perspective. You have to be somewhere at 257. You get there at 241. Shuttles run every 10 minutes. So since the ride takes 13 minutes, that means that you only have about a 3-minute window to get on a bus and still make it to your destination on time. So 30% probability, 30% chance. Now that's how we're looking at probability on a number line or the length of something. Now we're going to be looking at probability with area, and realistically this is much more likely kind of a realistic scenario that you would be working with. What's the odds of you being in a certain part of a figure as opposed to somewhere else? So again, we're still kind of taking the idea of the part over the whole thing, and we multiply it by 100 to get the percentage. So here, what are the odds of me being or throwing something and having it landing in space M as opposed to anywhere else? So we have to look at the area of space M versus the area of the entire quadrilateral, and that's how we would identify the percentage there. So here is a pretty decent explanation, or a pretty decent example. We have a green, which is in the shape of a circle, meaning a green for a golf course. So if you're not sure what that means, basically is, when you hit your ball from where you started at, you're trying to hit it into the hole. Well, the hole is located on something called a green, which is kind of that really, really short mowed grass or whatever. It doesn't even really look like grass, but because it's so short. But anyway, so here is an example. There's a section on that green that there's a prize that if you can hit your ball and get it in that spot, there's a prize that you can win. So we want to know, what are the odds of you getting your ball in there. Now, of course, this isn't taking into account maybe somebody's athletic ability of actually hitting the ball and getting it to the green, or how many opportunities you have to try and do something like this, because the more times that you have an opportunity to do something, it changes the probability of something happening. But so let's just say a better example of how you would do this would be like if you could actually stand above it and have a small version of this on your desk or something, and you stand above it and drop like balls of paper on there and see what are the odds of it landing in that white spot as opposed to the big circle. So we need to know the area of the two shapes. Well, the area of the circle is pi r squared. So we substitute the radius of the two circles there. So 7.5 for the small one, 37.5 for the big one. Find the indicated square both of them and just simplify the ratio. Now in this case, pi really doesn't matter, because even if we left our answers in terms of pi over pi still simplifies to be 1. So it really doesn't matter. We're just comparing those two numbers and that simplifies to be 1 over 25. So 1 over 25 as a decimal number, or as a percentage, would be only 4%. So randomly just throwing something on there, there's a 4% chance that it's going to land in the area that we want it to, as opposed to anywhere else on that circle. So at this point, ladies and gentlemen, go ahead and pause the video and work out these 3 examples on your own based off of what we've already talked about in the lesson. When you're ready, go ahead and hit play again to come back and check your answers with mine and to listen to any explanations that I give. So go ahead and pause the video now and hit play when you're done. Okay, so hopefully it didn't take you too long to get the answers for the 3 here. So problem number 1 was the probability that a point chosen at random on segment LP is also going to be on segment MN. So again, we're looking at a part versus a whole. So the length of MN is the part, the length of LP is the entire segment that we're talking about. So MN is 3 units long, LP is 12, that simplifies to be 1/4. So there's a 1 in 4 chance or a 25% probability of randomly selecting a point on point that will be on essentially both points, MN and LP. In example 2, suppose you arrive at your pickup location a little bit earlier. You arrive at 2:31 as opposed to 2:41. What is the probability that you can get to town by 2:57? Well, by getting there earlier, you're giving yourself more time at that 10-minute window where the shuttle is going to wind up picking you up at. So you have still 13 minutes that it takes you to drive to your destination. So you still need to be there, but you have to leave by 2:44 in order to be able to get to your destination on time. Well, out of that if you get there at 2:38 and you have to leave by 2:44, that gives you 6 minutes of waiting time. So within that 6 minutes, you're hoping that a bus or a shuttle is going to show up. So that gives you a ratio of 6 minutes to 10 minutes, which would be a 60% chance of within those 6 minutes, a bus is going to come by or a shuttle is going to come by and pick you up and take you to your destination. So the last one here, on the green in example 3, the hole is 4¼ inches in diameter. Find the probability that your ball stops in the hole. So essentially this is kind of like saying you hit the ball and you get a hole in one. And so it doesn't just go on the green, it doesn't just go on that circular area. It goes in the hole and you get to say, yeah, I did the impossible and I get to move on. Now, one of the things that you hopefully paid attention to here is that they're giving you these dimensions in inches, where the dimensions of the circles in example 3 were in feet. So the first thing you need to do really is convert all of the dimensions from feet into, there we go, from feet into inches. So the radius of the hole that the ball would go into would be 2.125 inches. The radius of the green would be 450 inches. So when I compare those as a ratio, that's, you square the 2.125 and you square the 450 inches. And so that ratio, when I multiply that by 100, is 0.002%. So that's the probability of you dropping your ball into the cup in one shot. 0.002%. Not very high. That's why I guess they celebrate so much when golfers get a hole in one, but I don't play golf, so it's kind of hard for me to get excited about it. But anyway, moving on. Example 4, property. The property owner here has this land. Again, you're kind of looking at it from a perspective above. So you have this space that's grass, you have this space that's water. Maybe it's just a field. Maybe they're thinking about building something on here. I don't know. But a homeowner's property is shown in the drawing. What is the likelihood that the deer is going to be in the grass? If there's an equal possibility, the water's not very deep, so the deer can go in the water. What's the likelihood of the grass or of the deer being on the section where the grass is? Well, that means, again, if we're going to compare, if we want the probability, we have to know what is the partial area and what is the total area. Well, the area of the grass is roughly 32 square units, because you can kind of look at it here and say, oh, well, this is a little rectangle here where one side is 4, one side is 8, so that's roughly 32 square units. I don't know what dimension that they're using, so units. So now we have to know what's the total area. So, well, you can kind of count all of the kind of stuff here. You can count all those squares, and all of those squares together are going to be about 44 squares. Okay. Uh, so we want to know, well, what is, let me pick another color here. What's the area like in this spot here and in that spot there? And we're going to have to kind of estimate a little bit, and they don't do a super great job of estimating it uh, because when you get down to it, we're really going to start looking at this stuff area under a curve, so to speak. Here they're kind of, let me pick one where you can see it. This region here, they're kind of looking at it as a triangle, where this side is 1, this side is 2, and we can find the area of that. So they're kind of saying that the uh, area here is about 1 square unit. And then they're going to kind of use like a little, I don't know if they're going to use like another triangle here, and then maybe a trapezoid here, and then maybe a little bit of a rectangle there. But they're just using basic shapes to estimate the area of an irregular shape, something that's going to have curves to it that's not necessarily a polygon. But ultimately, they're showing us that we have about 47 square units between the grassy area and the water area. So now that we've established what the partial area is, with the area of the grass, and what the total area is, the grass and the water together, we can say we have a ratio of 32 to 7. So when I simplify that, that gives me about 68%. So there's, almost a little bit better than two-thirds chance that the deer is going to be on the grass. So here, this last example, do the same thing, but now tell me what the probability that the deer will be in the water. So go ahead and pause the video, work this problem out, and when you're ready, hit play again to check out my answers. All right, so hopefully we have pretty good answers here. Looking at this one, we're still comparing the partial area to the total area. So that the area of the water works out to be about 15 square units, so that we're still looking at the overall area of 47 square units. So 15 over 47 as a percentage is almost 32%. And you also could have gotten that by simply subtracting the other area from 100, and you could have gotten this percentage as well. So the percentage that we got before, you could have subtracted that from 100, and we still would have gotten this percentage, because there's only going to be one of those two. But I didn't want to demonstrate it that way because we're practicing how we find the percentage by saying the part of something versus the total area. So that's it, ladies and gentlemen. The talking about probability. And keep in mind, this is a very simple idea of probability. Probability can get quite complicated when you're talking about counting techniques, and when the kinds of probability when they say what are the odds of somebody winning the lottery, or what are the odds of somebody getting bitten by a shark, or those kinds of things. Those things get really, really complicated. But this is pretty straightforward. We're going to just be comparing the part of something to the entire thing, and then multiplying it by 100 to see what is the percentage of that happening. But that's it, guys. If you have any questions, let me know. Until next time, thanks for watching. Take care.